and Dr. Kim for arranging this seminar at an odd day. So I will talk about combinatorial Laplacians and high-dimensional tree numbers. So this topic belongs to what we can refer to as a topological combinatorics, which means that we use topological tools to approach combinatorial problems. So in this talk, what we're trying to do is to give you a brief survey of what has been happening in the realm of combinatorial Laplacians in trying to generalize the notion of spanning trees for a graph to high-dimensional spanning trees for general simplicial complexes. And why are we interested in those things will become clear as we proceed. So let me start with the definition of a combinatorial Laplacian. So what we need to have in order to talk about a combinatorial Laplacian is a chain complex. So chain complexes that arise from simplicial complexes or a CW complexes or any other chain complex that you're interested in can be used for the definition of a combinatorial Laplacian. So we have the boundary operator from the ith chain group to the I minus first chain group, and its transpose is what we refer to as a co-boundary operator in algebraic topology, but it turns out that practically it's just a transpose of the boundary operator, and as such we think of it as a map from Ci minus 1 to C sub I. So there are two ways to combine these boundary operators to make it into a self map, so to speak. So the first one is called the up-down operator, and the second one is called the down-up operator. And when you combine those two, it's called a combinatorial Laplacian. So we'll see why this combinatorial Laplacian comes up and how this can be used in place of the usual, say, the graph Laplacian in addressing the notion of the number of spanning trees, for example. So one motivation for considering the combinatorial Laplacian is the analog of the matrix tree theorem, which is done by Temperley. He is a statistical physicist, and he gave a formula for the number of spanning trees using the combinatorial Laplacian, and the determinant turning out to be n squared times the number of spanning trees in G. So n is the number of vertices in this. So the question is, can we look at the combinatorial Laplacian in the general dimension, and can we understand what the determinant is going to tell us in general?
So here you think of the graph as a one-dimensional complex.
That's right.
This is the regular boundary operator.
That's right. Yes. So in graph theory, the del 1 would be called the incidence matrix. Yes.
So can you give concrete
example?
The definition of boundary 1, for instance, for graphs?
Oh yes, I will talk about that.
Right.
I have an example that's going to come up.
Okay.
So this is a plan of the talk during the next 55 or so minutes. So I'll talk briefly about the history of combinatorial Laplacians, and the analog of the matrix tree theorem, which is a Temperley's tree number formula using the combinatorial Laplacian, will be discussed a little. And then we'll discuss the notion of high-dimensional trees, and then we'll talk about how to compute the high-dimensional trees in many different kinds of complexes, including the matroid complex. So the matroid complex turns out to have a very interesting description for the tree numbers, so we'll talk about that briefly. So here's a list of previous works. The first time the combinatorial Laplacian was used in the context of analyzing simplicial complex is known to be by Ekman in 1945. And then there's Temperley's tree number theorem formula, and then the Stevenson and Zelen, so information centralism. So this is a topic that I talked about 4 years ago, right in this room in 2010, when I talked about the information centrality. And then after that, at around 1990s or so, the notion of high-dimensional tree numbers came up. So there are a few authors who talked about those things. And then there is Friedman's chessboard complexes, and also myself and Reiner and Stanton also talked about the combinatorial Laplacians of the matroid complexes and what the eigenvalues are and what the multiplicities of all those eigenvalues are and so forth. Now, an interesting development within the last 10 years or so is by Carlson and Zamorodyan. And they started talking about what's called the persistence homology. And this is part of the topological data analysis. And this is another very interesting topic that I would like a lot of people to be interested in, because I think this is a very prominent topic to be explored in the near future. And recently, Duval, Clevens, and Martin, they are the ones who really explored the notion of a matrix tree theorem in the higher dimension. And then recently, Professor Hyuk Kim and myself also talked about the logarithmic version of the tree numbers. So, in this list of topics or authors, the notion of tree comes up quite a lot, as you can see. And also the Betty numbers and persistent homology. So this is very much a topological combinatorics, so to speak. So let's talk about from the beginning, that is delta 0. So delta 0 is the combinatorial Laplacian in dimension 0. So let's say we have a graph, finite graph with n vertices and m vertices. So think of it as a one-dimensional simplicial complex or one-dimensional CW complex, as you like. So the chain group in dimension 1 is a free abelian group of rank m, and chain group in dimension 0 would be free abelian group of rank n. And the instance matrix is the boundary operator. And then we also consider the augmentation going from C0 to another copy of integers. So del 1 is the instance matrix. I will talk about an example in a minute, a more concrete example. And del 0 is an augmentation defined by the following matrix. So C0 is a free abelian group generated by the vertices, so to speak. And C1 is a free abelian group generated by the edges, oriented edges. Now, the so-called graph Laplacian is then the composition of del 1 transpose and del 1. So that's the graph Laplacian that we talk about in graph theory. But the combinatorial Laplacian, on the other hand, uses not only the graph Laplacian, but also the down-up portion of the combinatorial Laplacian, which is constructed by del 0. But del 0 is simply enough to see what actually happens in this case. So that portion is what we refer to as a J matrix, and J is the n by n all ones matrix. So it's a small change, but that change does a lot of things. So for example, so here's the graph Laplacian for K5. So all the diagonal entries are 4s, and all the off-diagonal entries are all -1s. But then as soon as you add J matrix, it becomes a diagonal matrix. So it's much simpler. And another advantage is that the graph Laplacian is always singular. So if you want to do something with this, it becomes sometimes very unnatural, whereas the combinatorial Laplacian is always invertible as long as the graph is connected. So the difference between those two algebraically may be small, but the effectiveness and also the applicability is quite huge. So the central theme of today's talk will be spanning trees. So let's just take a look at what a spanning tree is. So spanning tree of a connected graph first has to be connected. So the picture shows two examples of spanning trees. And the spanning tree has to be acyclic, means that there's no cycle in the spanning tree. And also, a spanning tree has to have n-1 edges, where n is the number of vertices. Now, another fact that one can get out of those three facts will be the item number 4, which says if you add a new edge from outside the spanning tree, it's going to contain a unique cycle. containing that edge and also other edges in the spanning tree. So we'll denote the number of spanning trees in a graph G by kg. So k is used because sometimes the number of spanning trees is called the complexity of the graph. So for that reason, kg is sometimes used. And very well-known result is the Cayley's theorem that says for the complete graph on n vertices, the number of spanning trees is n to the n minus 2. Now, towards the end of the talk, we'll see why this minus 2 appears in a more bigger picture. So that minus 2 is not just an accident, but it's going to appear over and over again in more bigger classes of simplicial complexes. So as Professor requested, here's an example of the incidence matrix. Say we have the following graph with 4 vertices and 5 edges. So the incidence matrix, the rows are indexed by the vertices, hence 4. What is it?
We have a sign.
How are you directing these edges?
Oh, I'm just directing the edges from the low vertex to high vertex. So, yes, so E1 goes from 1 to 2, and E2 goes to 1 to 4, and so forth. So we don't need to talk about arbitrary, artificial orientation. So the rows are indexed by the vertices, and the columns are indexed by the edges. So for example, the third column talks about E3, and the tail is 2 and the head is 3. So for the tail we get minus 1, and for the head we get plus 1. And we want to take the following point of view, that is, we want to think of this as made of 4 rows. So the graph Laplacian, which is the del 1 times del 1 transpose, will then be a matrix, 4 by 4 matrix, with entries Ri dotted with Rj, the dot product, so to speak, of the rows. So that gives us the following matrix. So the diagonal entries will always be the degree of the vertex, and the off-diagonal entries will always be minus the number of edges between the 2 vertices. So this does not have to be a simple graph. It can be any graph, any multigraph, and a similar construction may be applied. So let's talk about how to compute the number of spanning trees using the instance matrix. So this portion is going to be essentially a review of matrix tree theorem, which I'm sure everybody has seen. However, the ideas that goes into the proof of a matrix tree theorem will be directly extended when we talk about the high-dimensional spanning trees. So we'll review this fairly carefully. So G is a connected finite graph with n vertices, and to define a spanning tree, we think of it as a collection of edges, a collection of n minus 1 edges. Now let's take a look at the incidence matrix. Now, incidence matrix contains everything that you want to know about the graph. So in other words, if you have a graph, you can get the incidence matrix, and from the incidence matrix, you can get the graph back. So it has everything you want to know. In particular, it turns out that the collection of edges is a spanning tree if you restrict the columns to the corresponding edges, and that collection has the same rank as the entire matrix, entire del 1. So for example, I chose a spanning tree consisting of E2, E4, and E5, and if you collect those 3 columns, then they have rank 3, which is the rank of the del 1 in this case. So that's how you can recognize a spanning tree out of this matrix. And that is the crucial information about how to detect spanning tree linear algebraically, so to speak. And for the matrix tree theorem, we need to do one more thing. So this del 1 hat is the matrix that's obtained by deleting one row. So in this case, I deleted the last row. And what you do now is del B hat, which is a restriction of the deleted version of del 1 to the columns that correspond to the spanning trees. Then it turns out that if you strike out a row and collect the columns corresponding to spanning trees, it'll always be a square matrix. The numbers turn out just right to make this a square matrix. And furthermore, the determinant of this is going to be a plus or minus 1 if B is a spanning tree and then 0 otherwise. So this is the real essence that goes into the matrix tree theorem. So before I state the matrix tree theorem, let's take a look at two lemmas from linear algebra that is going to be used in that theorem. So the so-called Cauchy-Binet theorem talks about, this is really just a generalization of a dot product. If you have two vectors and if you form a dot product, then what you do is you multiply the corresponding components of the vectors and then add, and that's the dot product. Now, in general, if you have a rectangular matrix, then what we do is we multiply the corresponding sub-square matrices, or the determinant of those sub-square matrices, and the sum of that is going to be the determinant of the product of the two matrices of the same size. And the pseudo-determinant of a matrix, of a diagonalizable matrix of rank R, is a product of all non-zero eigenvalues of M. So that is the definition of the pseudo-determinant. So if a matrix is invertible, then the pseudo-determinant is the same as the determinant. But if it's not invertible, then a matrix has 0 eigenvalues. So forget about those 0 eigenvalues. Just look at the non-negative eigenvalues, and the product of those is what we refer to as the pseudo-determinant. And that can also be realized as a sum of all principal minors of order R of M. So in other words, you look at the submatrices of size R by R that is symmetric about the diagonal, and compute the determinant and take the sum of that, and that is also equal to the pseudo-determinant of the matrix. So here are three different versions of the matrix tree theorem. So the first version is the following. So L of G is 0, so that is what's called the reduced graph Laplacian. So in other words, what you do is take the graph Laplacian as we saw an example and strike out the row I and the column I. And then if you take the determinant, it's going to give us the number of spanning trees. And the proof is sketched here. The reason being by the Cauchy-Binet theorem, and also using the fact that if you restrict the del1 to the spanning trees minus any row, then the determinant is plus or minus 1 if and only if that restriction corresponds to a spanning tree. So every spanning tree contributes 1 to this sum. And if it's not a spanning tree, it doesn't contribute anything. So it ends up giving us the number of spanning trees in the end. Now the second version says every cofactor of LG is equal to KG. So what it means is that the reason why this is true is not particularly because of we're talking about the spanning tree, but this is more of a linear algebraic fact. That is, if you have a matrix that is symmetric, and also the sum of entries in each row and each column is going to be 0 for LG. And if a matrix satisfies that condition, then every cofactor is automatically the same. So this is a linear algebraic fact. And also the pseudo-determinant of LG, the rank of LG is n minus 1, where n is the number of vertices. So pseudo-determinant will be the sum of principal minors of size n minus 1, but each principal minor counts the number of spanning trees, and they're precisely n principal minors of size n minus 1, so that ends up giving us n times kg. So the reason why we have these three different versions is because LG is not invertible, and we have to do something to remedy that. So that is by deleting a row and column before we take the determinant. However, temporally show that deletion is going to be unnecessary, because you can just add the J matrix, and if you take the determinant, then you get a bit more than kg. The extra factor is n squared. However, that can be easily remedied by dividing both sides by n squared if what we're interested is in kg. So let's take a look at the proof very quickly. So here we use the multilinearity of the determinant function. And also the fact that J matrix has rank 1. So we think of this LG plus J as made of n columns, where each column is C1 plus the one column vector. One column vector means a column vector where every entry is 1. And the second column will be C2 plus 1. So C1, C2, and Cn, those are the columns of LG, and the ones are the columns of J. Now use the multilinearity of the determinant function to write this as a sum of 2 to the n determinants. So in this case, xi will be either ci or the one vector. But the point is that J matrix is rank 1, so you cannot have two copies of 1s. So only those ones that survive will be when only one copy of 1 exists. So if you expand the matrix along that column, what it'll do is to pick up n copies of the cofactors. So that gives us n copies of kg, and that I goes from 1 to n, so that gives us n squared times kg. So this is going to be much easier to deal with than the graph Laplacian. So if you recall the combinatorial Laplacian for K5, all the diagonal entries were 5. So the determinant is going to give us 5 to the 5, and according to this, then the Kg will be 5 to the 3. So that's a confirmation of the Cayley's theorem. In fact, the Cayley's theorem can be proved by using this formula very easily. So let me just remind you what I talked about 4 years ago. So because this LG plus J is invertible, now let's see what it can do when we take the inverse matrix of this. And the inverse matrix, we decided to call this combinatorial Green's function. The reason is that for the graph Laplacian, again, you cannot have a direct inverse, but you can restrict the matrix and try to consider the inverse of that restriction, and those things are called a discrete Green's function. So instead of looking at that, we don't need any restriction. We can just take the matrix and then look at the inverse matrix and call that combinatorial Green's function. It turns out that nobody used this expression before. So this combinatorial Green's function specifically refers to this matrix. So in 1990, Professor Carsten Thomason, who also visited here in 2010, he showed that the effective conductance or the effective resistance can be computed using the entries in this combinatorial Green's function in this fashion. And that also has a very nice combinatorial interpretation as being the quotient of two tree numbers. So one is the tree number of the original graph, and the denominator here is the tree number of the contraction of the two. So an interesting fact is that then the conductance or the resistance, which we think of this as an product of electrical flow is really just a combinatorial object in some sense. Now another interesting application of this, which came just 1 year before Professor Thomason's result by Stevenson and Zelen, and so Stevenson is a professor in anthropology at Harvard, and Zelen is also a professor from School of Public Health at Harvard, and they teamed up to talk about the network of baboons and trying to understand who is the real boss. So they constructed a network where the nodes are the baboons, and the edges will be weighted by the number of contacts that's made between two baboons. And he defined what's called the information centrality, but in the end, after this long paper that describes what it is, it turns out to be exactly identical to Thomason's description of effective conductance. So the effective conductance in the electrical network is in social science what we refer to as the information centrality of an edge. Again, the point of this slide, this part is that all these things are made possible because this matrix is invertible. There are ways to get to these results using the graph Laplacian, but this is, I think, the most effective and easiest way to understand what these identities, these quantities mean. So now let's move on to higher dimensional setting. So in order to do that, we need to look at the properties of the combinatorial Laplacian a bit more carefully. So we'll introduce the notation Li for the up-down portion of the matrix, and the down-up portion of the matrix J sub I. So this is in analogy of the graph Laplacian LG and the J matrix that we looked at. So first of all, the multiset of eigenvalues of this combinatorial Laplacian is a disjoint union of the eigenvalues of Li and Ji. So in other words, find the eigenvalues of Li and find the eigenvalues of Ji and take the disjoint union of those two. So in other words, do not maintain the multiplicity, and that is going to be the multiset of positive eigenvalues. Now let's take a look at why that is so. So Li and Ji, they're non-negative first of all. And Li and Ji commute because by the property of the boundary operator, when you compose the two operators upstairs and downstairs, that's always going to be 0. So that forces these two to be 0. So in particular, they commute. So they are simultaneously diagonalizable. So if you call the eigenvalues of Li lambda t's and the eigenvalues of Ji as mu t's, then the eigenvalues of delta I will be lambda t plus mu t. But because of this property, the product of this lambda t and mu t has to be 0. So they cannot both be non-zero. So that implies either this or that has to be 0. So in other words, the eigenvalue, so when we look at this expression, it's always going to be either lambda t or mu t. It will never be lambda t plus mu t. It is, but one has to be 0. So that's where that result comes from. So what it also tells us is that the pseudo-determinant of the combinatorial Laplacian is a product of that of Li and that of Ji. So this gives us a very convenient description of what the pseudo-determinant of delta I is going to be. So let me just mention that when we looked at the third version of the matrix tree theorem, this part is implicitly used in concluding that the pseudo-determinant of LG is n times kg. Now another portion that we need to check is so-called the combinatorial Hodge theory. So combinatorial Hodge theory relates the homology group with the harmonic classes. So let me remind you the definition of homology group. So ith homology group is the kernel of del I modulo the image of del I plus 1. Now I'll try to make the discussion as light on homology as possible, because the point of the whole talk is to understand the analogy between the matrix tree theorem and the higher dimensional tree numbers. And the homology is necessary to define the higher dimensional trees. However, I'll try to make it as light as possible. So the combinatorial Hodge theory says that the zero-dimensional eigenspace of delta I is isomorphic to the homology group. Now, why do we need this property? Because when we talk about high-dimensional tree numbers, we will define tree numbers in terms of homology, and in most of the dimensions, the homology group will turn out to be 0. So in the definition, and that's good news, because if the homology is 0, then the zero eigenspace will be also 0, which means that delta I will be invertible. So that's the real use of the combinatorial Hodge theory. The proof is fairly straightforward. It's just a rank counting, and there is nothing secretive about this fact. So I will just mention that the zero eigenspace of delta I, which is called the harmonic classes, is isomorphic to the homology group. So this is the real fact that we'll be using. If the homology group is either zero or finite, then the combinatorial Laplacian will be a non-singular matrix. So let's define high-dimensional trees. So first of all,
Excuse me.
yes,
Can you go back on? No, I want to see the last one.
yes.
Looking only at the reduced homology of
Yes, we always use a reduced homology, yes.
C is finite.
This is finite, yes.
Okay. And here I should think of this delta I as, in your notation it seems I should think of it as a matrix, right?
As a matrix, yes.
Obtained from the complex.
That's right, yes.
So is there an example?
Example of zero
So you
I.
showed an example when the complex was a graph.
Right.
Can you show me an example when I don't see how to write down this matrix when I have a two-dimensional complex?
Oh, I see. Okay, maybe I should.
Triangle in
Yes.
edges.
I'll just take a tetrahedron. I'll take a tetrahedron.
So this will have a chain complex that starts from C3 and all the way down to this. So for example, if you want to look at this portion, then what we need to do is to label the four triangles. So C1 is the one that has, for instance, 1, 2, and 4, and C2, I mean sigma 2 will be the one that has vertices 2, 3, and 4, and sigma 3 will be the bottom triangle, C4 will be the back triangle, for example. And we also need to label yeah, so I'm doing this lexicographically.
Yeah, so
And then, do you see it now? Yes. So if you take the triangle and if you do the boundary operator, then obviously this is going to be a 6x4 matrix in this case. Yes.
But you had a sign like 1
Yes,
minus
yes,
1
yes.
in the instance matrix. Here, do you have?
Yes, I do have a sign because, for example, for sigma 1, we think of this as an oriented triangle where orientation can be given any way you like, but I typically give an orientation that's natural, that is lexicographic, for example. So sigma 1 can be viewed as 1, 2, 4, and sigma 2 as sigma 2 as 2, 3, 4, and sigma 3 will be 1, 2, 3, and so forth. So if you apply del 2 here, then this will give us a following. So here 2, 4 is an edge, and also 1, 4 is an oriented edge, and so forth. So this is the typical definition of the boundary operator, how it's done. So one can always make a matrix representation of a boundary operator for a finite simplicial complex, or even CW complex. Yes. So this is all linear algebra, by the way. I should have mentioned. Yes. So any other questions before we launch onto the definition of the high-dimensional trees? Okay, so high-dimensional trees will also be defined linear algebraically. But before we do that, we don't talk about high-dimensional trees for any old simplicial complex, at least at the moment. But we talk about high-dimensional trees for a special kind of simplicial complex that we can view as a generalization of a graph. So that complex I decided to call it the gamma complex because gamma corresponds to G in English alphabet, and I thought that was a natural choice. So a gamma complex is a finite cell complex, or for the purpose of the talk, we can think of this finite simplicial complex, satisfying the following two conditions. One is that the boundary operators cannot be zero. They all have to have rank strictly positive. And the homology, the reduced homology of the gamma complex in all dimensions but the top has to be zero. So this is a generalization of a graph, because a connected graph, because for a connected graph we only have del 1 essentially and del 0, and they're obviously non-zero. And for a connected graph we have h1 may be non-zero because there may be cycles in the graph, so h1 may be non-zero. However, h0 has to be 0 because we're thinking of a connected graph. And the reduced homology in dimension 0 precisely counts the number of connected components. So that components minus 1. So we will consider this type of simplicial complexes as a generalization of a graph, and we will talk about the high dimensional trees for this type of complex. And we'll see there are plenty of examples that satisfy this condition in combinatorics that will be of our interest. So in particular, what it means is that by the combinatorial Hodge theory, the homology being 0 forces the combinatorial Laplacian to be non-singular. So in fact, these two are equivalent conditions. And so homology being 0 allows us to use the inverses of the combinatorial Laplacians, or simply consider the determinant rather than the pseudo-determinant. So just notations. So for a gamma complex, we'll denote a gamma sub I to be the set of all I-dimensional cells or simplices, and gamma superscript parenthesis I is the I skeleton. So I skeleton means is the collection of all the cells from dimension 0 up to dimension I, including those in dimension I. So for example, for graph, gamma sub 0 would be just a collection of vertices, and gamma sub 1 will be a collection of edges. And here, gamma superscript I, the 0 skeleton is again just a collection of vertices, but one skeleton will be the entire graph. And as before, we think of the rows and the columns of the boundary operator as being indexed by the cells in dimension I minus 1, and the columns indexed by the cells in dimension I. So here's the definition of high-dimensional trees. So recall that when we looked at the del 1, the incidence matrix for graph, we were able to recognize a spanning tree because if we look at a spanning tree, and if you look at the corresponding columns, those columns have to form the full rank of submatrix. So we use precisely that notion to define high-dimensional trees. So what we do is, first, let's say the rank of, so say the rank of del I is, say, R sub I. And we choose I-dimensional cells, and we look at the restriction of del I to the cells or simplices corresponding to the ones in the chosen subset capital B. If that rank is the same as the original del I, then we call that an I-dimensional spanning tree. So this is a very natural definition.
So here the script I is missing?
Right, yeah, so script I is missing because B is supposed to be I cells anyway, so that itself contains that information. So I didn't have to repeat that. So we also use the script I to be the collection of all I trees in gamma. So basically, the I-dimensional trees for gamma complex can be recognized from the boundary operator del I. So the homology of high-dimensional trees can also be understood as an analog of the homology of a spanning tree. So spanning tree is acyclic and connected. So when you look at the homology of a spanning tree, it's going to be all 0. the reduced homology all 0. However, in the case of a high-dimensional tree, there is a little variation. So first of all, this gamma sub b is defined to be the collection of I simplices that qualify as an I-dimensional tree plus all the lower skeleta. It's the same as saying that a spanning tree, you can think of it as a collection of edges, but also the physical spanning tree can be also considered as those edges plus the vertices. So it's the same type of way of thinking. So I simplices plus all the lower skeleta. So by definition, the gamma b will have a top dimensional homology to be 0 because by definition del b has the same rank as del I, so the kernel has to be 0. You cannot have kernel. And if you have dimensions I minus 2 or lower, then the reduced homology of gamma b is the same as the reduced homology of gamma itself because they share the same skeleta from dimension I minus 1 and below. But the problem comes when you look at I minus 1 dimensional case, which does not happen in the usual spanning tree for a graph. So first of all, the definition of homology will be kernel of del I minus 1 modulo the image of del b. But by the definition of gamma complex, this kernel of del I minus 1 is equal to image of del I. So we end up looking at the quotient group of those two objects. But del I and del b, they have the same rank. So if you are forming a quotient group of two free abelian groups of the same rank, then it's a finite group, it's a torsion group. So it turns out that this object can be finite and all the other homology groups will be 0. So this is a characteristic in some sense of this specific spanning I-dimensional spanning tree. So let's take a look at an example where this I minus 1 dimensional homology is going to be non-trivial. And the prime example will be the real projective space. So the first standard simplex. So this is 5-dimensional standard simplex and the 2 skeleton, but vertices 1 through 6. So notice that in order for simplex to be 5-dimensional, you have to have 6 vertices. And this 2 just means the 2 skeleton, which means that we want to include all the triangles that you can get out of these 6 vertices. So there will be 20 triangles. So you have 6 vertices and 15 edges and then 20 triangles. So that's what this complex is. And in this complex, we can pick these 10 triangles. And it turns out that this collection of triangles satisfies the definition of the high-dimensional tree. So the top dimensional homology and all the lower dimensional homology will be 0, but the middle dimension turns out to be Z mod 2. But that is okay because we already know that that could happen. And in fact, it turns out that this is a triangulation of RP2. And before the 5-dimensional standard simplex, this never appears. And this is the first dimension where this type of triangulation of RP2 appears. So the point is, this is an example of a 2-dimensional tree whose first homology group is non-trivial. Okay, so how do we define the high-dimensional tree numbers? In the case of a spanning tree, we only had to just add the number of spanning trees. And it turns out that that is going to be a very difficult combinatorial problem. In fact, that problem I don't think has been completely solved. However, instead of counting them as they come up, if we do weighted counting, where the weight of a spanning tree, I-dimensional spanning tree, is the size of that torsion group, and we define the I-dimensional tree numbers as a sum of all those torsions, size of torsions, then that at least takes care of the difference between the different spanning trees and the different characteristics of the spanning trees in I dimension. So for for the general I-dimensional tree numbers, we always use the weighted sum, weighted counting. And there's another reason why we want to do weighted counting, as we'll see in a minute. If you want to count the number of spanning trees using the combinatorial Laplacian, this turns out to be the correct definition. So for example, we can define k sub minus 1 as, define it as 1, and k sub 0 will be the number of vertices, and k1 is the usual number of spanning trees of the one skeleton, and so forth. And also k sub d will be 1 if gamma itself is an acyclic complex. So remember that we looked at this picture before. So this is how we reduce the instance matrix and look at the corresponding columns for the spanning trees, and then this turns out to be non-singular, and in particular determinant being plus or minus 1. So we need to do exactly the same kind of thing with this del I. That is, if you look at del I and say that the rank of that matrix is R sub I, then as a general linear algebraic question, if you have a rectangular matrix that is rank R, then you can always find a submatrix, sub-square matrix of size R by R that is non-singular. The question is, which one of those will be non-singular R by R square matrix? So that's a general linear algebraic question that we can ask. And in this case, it's not just any matrix, but this is a boundary operator. And it turns out that those non-singular submatrices are precisely those ones that you can obtain by strike out the rows that correspond to the I minus one dimensional spanning trees, and collect the columns that correspond to I-dimensional spanning tree. Now, if we go back to this picture one more time, that's precisely what we do in matrix tree theorem. We strike out a column, a row, and of course, a row corresponds to a vertex, and vertex is a zero-dimensional tree. And we select the columns that correspond to the spanning trees, which is one-dimensional tree. And that is precisely what's happening. So this notation, A bar, means those rows that are not indexed by R. So it's the rows that are outside, so to speak, the I minus one-dimensional spanning trees. And it turns out that these submatrices are precisely square, and also those are the only ones that are going to be non-singular in this setting. And what's also interesting is that the determinant of those sub-square matrices is the product of the weight of A and the weight of B. So this is very easy to remember. Now, in the case of a Spanish algebra graph, those WA and WB, those are all equal to 1. So that's why they did not look very interesting. But in the high dimensional case, they can be quite interesting depending on what the weight is. So this is the key to the counting of the high dimensional tree numbers, because after this, once we identify the exact value of these non-singular submatrices, then we can apply the Cauchy-Binet theorem, and we can apply the pseudo-determinant argument and so forth to get what the determinant of the entire combinatorial Laplacian is and how that relates to the tree numbers. So I just sketched a few main ideas of the proof. So first we show that the restriction del A bar comma B is non-singular if and only if those two are trees. I will not go through the details of this because it uses a long exact homology sequence of the pair, so to speak. And to get to the second statement, one is to use the long exact sequence to show that this homology group is the product of these two. And notice that the first factor here is the weight of A, and the second factor is the weight of B. So that's from the long exact homology sequence, but the third one is directly from the definition of the relative homology, which shows us that that item here is really just the determinant of that restriction. So those two are identical, and that gives us this result. So this slide shows how we can recap what we saw before in terms of this new language, so to speak. So the product of all positive eigenvalues of a graph Laplacian, which was n times kg, in new notation, the pseudo-determinant of L0 is the LG in this case, is K0, the zero-dimensional K-dimensional or tree number, and K1, the one-dimensional tree number. And temporalist formula also can be reformulated in this form. So the determinant of delta 0 is K minus 1, which by definition is 1, and K0, number of vertices, times number of spanning trees. So that is going to be that is going to appear in the pseudo-determinant and also determinant of this combinatorial Laplacians. So, for example, if you look at the Li part, so the up-down part, the pseudo-determinant turns out to be the K sub I minus 1 times K sub I, and the proof is almost identical to the case of a spanning tree of a graph, except now that this determinant is not going to be just plus or minus 1, but it has to be replaced by the weight of A and the weight of B squared. So that turns out to be K sub I minus 1 times K sub I. Likewise, so this is what we can refer to as a generalized matrix tree theorem. And also the next is the generalized temporalist formula. So the important item is the second one. So in the case of delta 0, we already saw that this is just a temporalist formula, but in general, delta I can also be expressed as a similar product like this. And again, the proof of second one is the more important one. And we saw that the determinant of delta I is going to be the pseudo-determinant of Li times Ji, but that using the previous slide, it's easy to see that it's Ki minus 1 times Ki times Ki plus 1. So Ki appears twice, so that's why we have the square there. So we've seen the generalization of matrix tree theorem and the temporalist formula. Now here's another interesting way to combine all these results into one single generating function, so to speak. So what we do is we consider the log of the determinant and also log of the tree numbers, and form a generating function for this omega I, the log of determinant, and also the generating function for the kappa I, which is the log of ki. Then those two polynomials are combined in this fashion. So this is very much like the temporalist formula, except this is a logarithmic version of it. The proof is very straightforward. All you need to do is that if you apply log to the determinant, then you can expand this as a sum, and you'll see very easily that this type of convolution happens. So in the case of an acyclic complex, the notion of tree numbers and notion of the determinant of the combinatorial Laplacian, they contain exactly the same information. So that is an interesting effect. And also I said that in the Cayley's formula, there's n to the n minus 2, and that is explained by this two. So for example, I'll talk about the tree numbers for the simplest case, which is the tree numbers of a standard n simplex. And we'll see that if we use this formula correctly, then the tree numbers for the n simplex is nothing more than the binomial theorem. So here's the work of Kalai in the 80s. So what he does is trying to compute the high-dimensional tree numbers on a standard simplex. So first of all, we need to look at the combinatorial Laplacian in each dimension. And it turns out that it's a fairly straightforward exercise to see that the combinatorial Laplacian is just a diagonal matrix with all n's on the diagonal, just like the combinatorial Laplacian for K5 as we saw. And it turns out that phenomenon persists in high dimensions for the standard simplex. So the determinant of this is going to be n choose I plus 1. Again, I plus 1 because I dimension means we're looking at the simplices with I plus 1 vertices, so that's why there's this one difference. So if you look at the log, if you take the log n, then it'll give us just the power, which is n choose I plus 1, and d of x, which is the generating function for the logarithms of the determinants, turns out to be just simple polynomial, x plus x to the nth power by the binomial theorem. But because of the previous theorem, we also know that k of x is just 1 plus x to the n minus 2. So 1 plus x squared is cancelled on both sides to give us this. So right from this, we can get the tree numbers. So the tree numbers, kappa sub I, which is log n of ki, will be then n minus 2 choose I. So that tells us that the tree numbers will be then n to the n minus 2 choose I. So notice that when I is equal to 1, that is precisely the Cayley's theorem. And in the general case, it's not much different. And the point is, all these things are made possible because of the logarithmic version, which really reduces the whole problem to just a binomial theorem. And because I only have about 3 minutes, so let me just point out that you can also get the number of spanning trees of a hypercube. Hypercube is also an acyclic complex. And all you need is the eigenvalues of the combinatorial Laplacian, and then use the dx equals 1 plus x squared plus kx, and you can get those tree numbers fairly easily. So the remaining 3 minutes, I just want to mention about, at least I'll describe the tree numbers for the matroid complex and some interesting invariant that appears in this description. So this is based on the work that myself and Rainer Stanton did back in 2000, where we talked about the integrality of the eigenvalues of the matroid complexes. So it turns out that for any matroid complex, the eigenvalues are all non-negative integers. And that is very rare. If you try to compute the eigenvalues of a combinatorial Laplacian on any small complex, it's very difficult to produce integers. But in this matroid case, they're all positive non-negative integers. And we need to combine this result with Bjorn's homology rank of the matroid complexes and also Crapos in a beta invariant of matroid. So let me just describe what it is that exactly is going to happen. So determinant of delta I for the matroid complex will be lambda to its multiplicity. So this capital lambda is the collection of eigenvalues of a matroid complex. So obviously a determinant has to be lambda to its multiplicity and the product of all those things. And in light of the theorem that we just looked at, we can expect the tree numbers to be expressed in terms of the same set of eigenvalues but a different multiplicity. So the question, one can also get a rough description of what this multiplicity is going to be by using one of the items in the theorem, and also by using induction. So it's a very simple result that you can get from this. So the question is, can we describe this a bit more concisely instead of this unorganized form? And it turns out that multiplicity of lambda in description of the tree numbers can be described as what's called the alpha invariant of a matroid, and the beta invariant of the quotient matroid. So this is going to be some form of a convolution of the alpha invariant and beta invariant. The alpha invariant is the homology rank of the matroid complex, which is well studied and which is well known, which unfortunately I don't have time to describe this in detail. So the point is that in the description of the multiplicity of the eigenvalues for the tree numbers, this beta invariant comes up very naturally as a convolution. So in general, the tree number for the matroid complex is a product of the same set of eigenvalues for the matroid complex itself, where the multiplicities is described as a convolution of alpha invariant and beta invariant. So I can talk about this after the talk. So this is a whole new topic about the topological data analysis. So I think I'll stop here today.